Now let us summarize what we learned. Okay. So finally you learned an addressing mode called register mode, right? Example, add R1, R2, R3, right? This is register mode. Absolute mode or direct mode. In absolute mode or direct mode, one of the operand is directly memory address. Okay. So if you specify one operand through a memory address, we say that that is absolute mode. Example, load or store, right? So load R1 with some memory location A. So here one operand you see, this operand is from memory, right? So we'll ask Mr. A, are you operand? No. The value in A is operand, right? That means what? A is not an operand. So to get the operand, we have to go to a memory address called A, right? So that's why such kind of addressing mode is called absolute mode. In the absolute mode, we are going to provide one memory address, and if you go to that memory address, we are going to get the operand. Such kind of addressing mode is called absolute mode or direct mode. Okay. Somehow your computer should understand that this is, absolute mode instruction. Okay. We will see how to differentiate them. Generally, so how you understand that this is absolute mode? Because, based on the pattern, we will see that later. That means how your processor understands is, so we will give different opcode for every addressing mode. Okay. We will see that later. So that is not a big deal. Next, immediate mode. In immediate mode, example was like adding R1, let's say plus 1, hash 1. Here R1 is R1 plus 1, right? So here if you see the operand, we have directly operand in the instruction itself. This is the instruction. In the instruction itself you have an operand, right? That's why such kind of addressing mode is called immediate mode. Now we will see indirect mode. These are all just names, okay? So in indirect mode, what is indirect mode? There are two indirect modes actually. We will see one by one. So in indirect mode, what are we going to do is, we are going to specify the operand indirectly, okay, not directly like absolute mode. So what is the difference between 2 and 4? We will see. For that I will give the story. This is your memory, okay. Assume that, let's say this is a memory address A, okay, 100 maybe. There is a value 5, okay. Now there is a register called R1. In that R1 you have an address of this memory location. What is the address of this memory location? 100, okay. Now, so see this instruction, load, example, load load R2 with R1. I give a different syntax here. Now what does it mean is, we have to load a register R2. That is pretty clear, correct? With what? This one, see the model, where R1, are we going to load R2 with R1? No, correct? R1 contains, here we will be providing R1's machine, some address 0001, okay. We will be writing like this 00001. But generally we write R1, assembler converts it into 00001, right? My intention is finally R1. Now here, are you going to move this R1's code 00001 to R2? Let's say, if you really move this 00001 to R2, then we say that the operand is that 00001, that is directly here, right? That means we are providing that. Then the addressing mode will become immediate mode, right? Okay. Second thing, but that is not my intention. Let's say, what is my intention is not moving 00001 to R2. My intention is moving 5 to R2. For that, what should I do? First I should go to 0001 address, then I will get 100. I should take that 100. Then after that, I have to load this 100's value into R2. Correct? After that, it should work like direct mode. Example, if I directly give this one, load R2 100, what happens? If it is direct mode, let's say your processor knows that it is direct mode, what it is going to do? It is going to take directly the value in the 100 and it will be moved here. Then R2 gets 5. Perfect. But I want to do it in indirect way. For that, what I do is, I keep 100 into a location R1, then I specify R1 like this, and to differentiate that this is a different addressing mode, I put the brace like this. Okay, now load R2 R1. Okay, so this brace R1. Whenever I write this one, my intention is this is indirect mode. In the indirect mode, so R1 contains address of the operand. Okay, so R1 here, which is mentioned in the instruction, that is not operand. Okay, now if you go to R1, do you get operand? No. If you go to R1 also, you don't get operand. But if you take that value which is in R1, and if you go to that value, that address, you will be getting a value that is going to be operand. So this is called indirect mode. Okay. Now what is going to happen because of indirect mode, we will see. What is the functionality of this indirect mode instruction, we will see. Load R2 with R1. Very simple. For that, first we should go to R1. Okay. Let us take this as 000001. Now here we will be writing 0001. Here it contains 100. Go to R1, fetch value which is 100, don't store into R2. Then that is absolute mode. Then go to 100 and fetch the value in the memory location 5 and store that into R2. So now finally in R2, 5 will be stored. Then we say that your instruction is in a mode called indirect mode. Okay, especially this is called register indirect mode. Okay, register indirect mode. Register indirect mode. Remember it. Now there is a one more mode called memory indirect mode. We try to understand that. Memory indirect mode. So what is memory indirect mode is, this is your main memory. In this main memory, you have, let's say, address A. A contains value 5. We will be doing like this, load. Okay, so I write B. In B you have address of A. For easy understanding, we'll give numbers like this. This is 100, this is 200 memory location. So B's content is now 200. Now we will be telling like this, my dear instruction, when you are executed, R2 should get 5. But I am going to provide you, address of B, that means B address. See. So here, this is, let's say, an instruction specially designed with indirect mode. Okay, this is indirect mode. Whenever I say this is indirect mode, what should happen is, B is not operand. Content of B is not operand. Okay, so first of all we should go to really execute this instruction, first we should go to B. It is indirect. This symbol indicates that it is indirect. Okay, just for, so anyway we can define. Okay, not a problem. Don't remember these details. In the question they clearly mention that, this symbol indicates indirect mode, whatever. Okay, now, so whenever this symbol is there, I am assuming that it is indirect mode, then I will go to first B to get the real address. First of all I will go to B, then I get 200. Okay, let me take it. Now that means finally I got what? 200. Now is it the operand? No. If it is operand, then that is direct mode. So since it is indirect mode, then we will be going to 200 again. When you go to 200 again, and if you fetch, then you get what? 5. That 5 should be transferred to R2. Try to understand. Okay, if you store 200 here, that addressing mode is called direct addressing mode. Correct? If you write like this, example, R2@B. When this instruction is executed, let's say R2 got 200. Now in the GATE exam they ask, what kind of addressing mode it is? Simple. So, are you directly, what is the address, what is the meaning of B here? Let us replace. B means 100. Okay. Now, did you store 100 here into R2 in the destination? No sir, I did not store 100. That means this is not immediate mode. In the immediate mode, we directly store 100, whatever is given in the instruction itself. Now, but what are you doing? We are going to address of 100 and we are fetching the value. Okay. Example, let's say 200. That means what? This is direct mode. Okay. Now, based on the functionality, I am just identifying the addressing mode. Third one. What if it is 5? Why it is 5? What happened? First of all, it was 200, right? When it was 200, then, sorry, it was first 100, right? Okay, whenever it is 100, then you changed it to 100 is changed to 200. That means what? You went to address 100 and you fetched some value. Again, you went to address 200 and you fetched another value. That means 2 times you accessed the memory, right? Then such kind of addressing mode is called indirect addressing mode. Of course, it's not a big deal to understand. Okay, so that is about indirect mode. In the indirect mode, it's like we will be accessing the memory 2 times, especially memory indirect mode. There is another variation called register indirect mode. We have seen already, right? In the register indirect mode, first time we will go to register, right? That will be the address of the register will be specified in the instruction. We will go to the register, you get a memory address, go to that memory, then you are going to get value. That model is called register indirect mode. The second model is memory indirect mode. So in memory indirect mode, so we will be first of all going to directly memory and we will be fetching some value that is not operand. That is going to be the address of the operand. So again you have to go to that address to fetch the value. So that is indirect mode, right? So memory indirect mode. But here already I told you, generally RISC architecture says that your instruction should take very less time. Such a way we should design that instruction. That's why memory indirect mode, whatever you discussed now, that is not generally part of RISC kind of instruction set. So that is a instruction part in the part of CISC instruction set. Okay, now and one more thing. So this question should not arise for you. What is that, sir? This memory indirect mode, is it used in Intel? Is it used in Motorola? So that's a separate story. We are not talking about them. We are talking about the instructions in a general sense. That means some typical instructions we are learning. So that that might be present in one architecture or not is a separate story. First for that we have to go through the architectures. I mean the particular instruction set. So we are not doing that. We are just understanding for a hypothetical machine. So I am assuming one hypothetical machine. For that I am defining register mode, absolute mode, direct mode, immediate mode, indirect mode. Especially in indirect mode, we are going to use only register indirect mode, but of course memory indirect mode also possible. Okay. Now the fifth one. So before going to that another addressing modes, first of all we will try to use these addressing modes. Already you understood how to use register mode, absolute mode, immediate mode, indirect mode, right? Let us summarize quickly. Register mode, your operand is directly in the register which is specified in the statement. Second one, absolute mode. So your one of the operand is directly a memory address. If you go to that memory address, then we are going to get the operand. So in either register mode or in absolute mode, your operand is not available. We have to go to that particular memory location to access it. Example, in register mode, we have to go to the register which is mentioned. Now in absolute mode, address of the memory will be given in the instruction. We should go to that to access the operand, that is absolute mode. So all these addressing modes are defined based on how you access the operand. Where is the operand? Third one, where is the operand in immediate mode? Directly in the instruction itself. Now, where is the operand in indirect mode? First of all, one address will be, something will be mentioned in the, instruction. Go there, but you don't get operand. If you get the operand, that is direct mode. You don't get. That means, so that one address will be mentioned. I'll show like this. One address will be mentioned in the instruction. This is part of the instruction, but that is not operand. Then if you go to that address, then we will get another address A2, but that is also not operand. It is again address of the operand. So the third time you are going to get the operand. Okay. To get the operand, so take the A1 and go to the memory location of A1. Then you get a value A2, that is again an address. Go to A2, then you get the operand. So such kind of addressing mode is called indirect mode. So here I will tell you the usage of indirect mode. Sir, why we use it? Because it is complex, right? Unnecessarily there are, there is one memory access, right? Plus one register access. And especially if it is a memory indirect mode, there are two memory accesses, right? But still why people use? The reason, so indirect mode can be used to implement pointers, especially, okay? Pointers can be implemented using indirect mode. C programming pointers or Java pointers, right? Of course. In Java there is no direct pointer concept, forget about that. So let's take C, any like C programming language. In C programming language we have a clear pointers, right? We implement pointers. So there should be assembly language support. Without assembly language, otherwise machine level instruction support, how can you implement pointers, correct? That's why definitely there is a support from your machine instructions, and that comes from a mode called indirect mode. Understand now? So register mode, absolute mode, immediate mode and indirect mode we have studied. We will be using them for one application. So before that, I will tell you one more thing. You need some instructions called branch instructions. Okay, forget about the addressing mode of branch instruction. First understand what this branch instruction is going to do. Typically, so already I told you these are all hypothetical machines instructions. This instruction might not match with any of the real processor's instruction set, doesn't matter. We are understanding the meaning, right? So branch if r greater than 0. Whenever I use this kind of instruction, what I am going to do is, so this is label. Here there will be one address. Typically that will be a main memory address. Okay. Now in this instruction, so one register is specified. That register will be compared against 0. If that register value is greater than 0, then we will go to condition will become true and we will go to a memory address which is nothing but label. Okay, like sir, what is label? What is A? It is a symbolic name for one memory address, correct? Similarly, what is B? It is a symbolic name which we use as a assembly level programmer to represent one memory address. Similarly, label is a symbolic name which represents one memory address. Okay. Now what we are going to do is, using this instruction, we are comparing one register with one value. Based on the value, we are directing the flow. That means, I will tell you. So we will be directly going to this memory address. Example, label's real memory address is 200. The label is our imagination. Okay. But label is nothing but 200. Then when this condition is true, we will go to 200. Now, here one important point I would like to tell you to understand this branch instructions. First of all, how these your machine instructions are going to be executed, I will tell you. Here again I am going to miss one detail. That detail we will see later. So when you write a program, let's say assume that you have written a program for C equal to A plus B. Okay, your program is simply C equal to A plus B. For that we have to define 3 memory locations, C, A, B, correct? So what is the assembly level program for C equal to A plus B is like this. First of all, somehow I don't show the syntax, but I will tell you like this. You have to define A. Okay, that means you should say that, my dear assembler, I want one memory location, but I refer with it with A, but you can give any memory location. Similarly, it is like writing in C level in C programming int A, B, C, right? Here what we do is, we simply specify like this. Now I want a memory location A, I want memory location for B. So how many bytes? Sometimes we specify the space also. Like example, I want 4 bytes of memory. In that way we will be specifying it. Again it varies from assembly level program, one assembly level to another assembly level. That means one machine to another machine. Remember one thing, every machine, example, what is machine here I am using so many times. So Intel people designed their own machines, right? Their own architecture they have. Similarly, ARM processors will have one instruction set and one set of processing. That means one functionality or one architecture. Similarly, Intel people will have their own architecture for their devices and one instruction set. Now when you write a program using ARM processor's instruction set, okay, that means you are writing a machine level program finally for ARM processor that might not work for Intel processor if you directly go and execute, because these two are different, right? This processor understands in a different way. Maybe this processor has an instruction add in a different way. This processor understands add in a different way. How it takes arguments, what kind of addressing modes it supports, it completely different, right? Example, add command is 010 in the machine level, okay, for one machine. So for ARM machines, let's say same add code is 100. Directly if you go to this machine and say 100, it cannot understand that it has to add, because to say in this machine add, we should use a code called 010 in the instruction. but you are using 100 because we were defining the things for ARM, correct? In that way, so every processor's instruction set will be different, their programming language will be different. That means their machine instruction will be different. If you want to have compatibility, then we have to write that program again here, correct? Otherwise, some other precautions we have to take. Yes, we can do it. So there is a emulation concept. So that things I am not discussing now, but just I am telling you the problems. Directly this is not possible. What is that? Writing one C level program or any program, otherwise directly machine level program, and directly taking that machine level program and going to other processor and executing it is not possible. Okay, remember it. So also known as exe file. So exe file is nothing but, generally in C programming terminology we use exe, right? That means we compile a program and we get executable code. That is nothing but set of machine instructions. But this exe file won't work for another machine because their exe model is different. That means these machine instructions are different from these machine instructions. But of course, for compatibility we can do some extra things, that is separate story. We don't bother about that now. Okay. Now what I would like to tell you is, example, let's say you have some processor and one machine instruction set. Let's say finally you have written one machine instruction program. Okay. Now, so that program is very simple. It is, I just, because it is very difficult to understand in machine instruction level, I don't show you machine instructions, but I show you assembly level instructions that will be automatically converted to machine. Okay. Now there is a quite direct conversion, like, changing add to, a code. Example, you write add R1, R2, R3. Then this instruction, assembly instruction, which we can understand, that can be converted very easily. For add, there will be a code word, okay, 0, 1, 0. That is defined in its machine instruction set. So 0, 1, 0. The assembler is going to convert add to 0, 1, 0. You write R1, but there is a binary code for that, like this. So register 1, 0, 0, 0, 0, 1. Register 2, 0, 0, 0, 1, 0. Register R3, 0, 0, 0, 1, 1. Sir, why only 5 bits? Simple. Since there are 32 registers, to uniquely identify them, 5 bits are enough, right? In that way, so we can generate a code. That means what? We can easily convert one assembly level instruction to machine instruction. That's not a big story, okay? But now we are not focusing on that part. What we are going to focus is how your program is going to be executed. Let us show here. You have, let's say, this main memory, and you have written C equal to A plus B code. Recall how you write it. Load load R1 comma A. Let us save the registers. Load R2 comma B. Then add R1, R2. Then store that R1 value into C, correct? Now remember one thing, already, so I have used some extra instructions in assembly level. I am not showing that, so that already, so one memory location is allocated for A. This is the memory location called A. This is memory location called B. This is memory location called C. Okay. So this is, I can say, your date variables in your program. But I have not shown, I will tell you later. So how to define this ABC variables. So there is some syntax you can understand. In C programming, how you define in the same way, here also we can define. So because of that, finally, when you write this program, what happens I will tell you. So these instructions will be loaded somewhere in your main memory. Assume that, let's say, your instructions are loaded here. Load R1 comma A, load R2 comma B, add R1, R2, next add, store R1 comma C. What I want to tell you here is, whenever you write this program and when you ask assembler, my dear assembler, so please convert that into machine instructions. Let's say these are the machine instructions, but I am showing in high level only. Please execute it. Whenever you ask that, immediately what your assembler will do is, though I am showing you in assembly level, let's assume that these are all machine instructions directly, okay, binary code. Now, so your machine will, your processor will start executing them. So what your assembler will do is, so it will, and here I would like to add one important point. Now let us introduce program counter. Sir, what is that, sir? Program counter is a general purpose register There are 32 registers. One among them is designated as program counter. Okay, that program counter always contains one address which is nothing but the starting address of your instructions. Example, let's say since your assembler loaded your program here, right? Okay, so assume that the memory addresses are 100. Now I am assuming that instruction set is RISC instruction set. So where every address is, every instruction takes exactly uniform number of bytes, 4 bytes. We will see one more thing in pipelining. Whenever your instructions are in a uniform way, that means their sizes are equal, like 4 bytes or 2 bytes, whatever, but they are equal, then in pipelining you are going to get the benefit. So pipelining is a concept, otherwise that is an optimization which is going to help you in executing instructions parallelly. That we will study later. For that, instruction should be in equal in size, remember it. Now I am assuming that's by simply here my each instruction takes exactly 4 bytes. Then one thing, right? Your system is byte addressable system. That's why 100, then 104. Your next instruction will start at 108, then 112, so on. Let's say this is 200, 204, 208. Now, what I would like to tell you is your assembler is going to first keep 100 in the program counter. When your program starts beginning, then we say that yes, your program started working now, executing. So now we will see the various steps. Now don't ask me, sir, how program counter gets 100? Assembler is going to assembler will have some extra program because of that program. So your program will be loaded like this in the memory. That we are not discussing. Okay, it's again same way. Like, so you are able to store some data in some locations, right? When using load and store, if you can store and fetch the data, in the same way assembler also can take your data as your instructions and it can load somewhere. Not a problem, correct? We have load instruction, we have store instruction. Using that, your assembler also can load your instructions like this. Let's begin here. That would be good, right? Now program counter is initially 100. What is going to happen is every time, so your processor is going to execute instructions like this. First, program counters will be accessed, that is 100, right? Then that 100 will be used as memory address. Directly your processor will go to 100 and it will fetch this instruction. Sir, why? Such a way there is a circuit called a control circuit, remember it. I will explain how that control circuit works. So your processor is designed such a way that always in the early morning when it starts, whenever that is switched on, it will blindly go to program counter. That's it, whatever it is written. And it will go to that memory and blindly, it's a uniforming, I can say that processor is designed such a way that it will follow the systematic rule. What is that is? Directly it goes to program counter. Whatever is there, it will fetch. Okay, that is the thing we are now studying now. Let us always remember how your processor works. It will take the value from program counter, and using that program counter, it will fetch the instruction. Okay, and especially it uses a register because we have to hold it, right? So we are going to load this instruction into a special register called instruction register. Such a way already processor is designed, remember. Okay, now so load R1A, load R1A, it will come to instruction register. Now we did not do, we did not progress much. Don't worry. So nothing I explained you. Up to now, you have a program, right? So this is the way already it is ordered using assembler. Now whenever processor starts working, then that processor automatically do these things. Step number 1, it will take the program counter and it will fetch the data in that program. What is the value is there in the program counter, it will go there and it will fetch it. That is called fetching. So it will fetch the instruction. If there are multiple, if your instruction occupies multiple words, then all that words will be fetched then. And we will be seeing these details again and again. Don't worry. This is not the first time and not the last time. Of course, this is the first time, but not last time. So second step what we are going to do is, what your processor will do is, it is automatic. For that it doesn't require any instruction. Remember one thing, there is a circuit called control circuit. So because of that control circuit, automatically, okay, that control circuit will work always such a way that automatically these things will be done. So many times I am repeating, right? Because this is very important, right? Now fetch that. So now you got that into instruction register. What is that? Load R1A. Now, then your processor will start understanding it. It will first see the opcode. That means operator. Okay, opcode. What is the operation? That is nothing but opcode. Now, based on that opcode, it will understand what to do again. So, automatically this control circuit will be connected to this load part. Then control circuit understands what are the devices should be enabled, because load means what? Something should be happen, right? Some functionality should be executed. Whenever there is a load, you tell me what should happen. You know that, right? What should happen? Register R1 should be prepared and memory address A should be accessed, right? A means here in the machine level it will be 200. So we have to go to 208 here. Let's say value is 5. Then we have to fetch that value and we have to store it in register 1, right? This is our expectation, but your processor is going to achieve it. Now you have a question, sir, how it achieves? For that there is always, there is a control circuit. At this moment, you don't know what is control circuit, right? Remember, control circuit is designed such a way that once, everything will be automatically done. Okay, first step, it will. So there you can imagine like this. Control circuit is like a brain. In the early morning when you wake up, okay, now what you do? Let's say you do brushing, right? So after that you do bathing, everything in that way, right? After that you take breakfast. Who taught us, right? Who told you that to do brushing immediately after that bathing, after that breakfast, right? So this is a sequence of operations which are already programmed. That's why in the early morning when you wake up, you do these activities one by one. For that no one will teach that, right? So similarly, here also what is going to happen is there is a control circuit. That control circuit is designed such a way that so there will be some systematic steps that will be performed because of the control circuit. It will tell like this, my dear processor, it's 9 o'clock. Now directly go to program counter and fetch whatever it is and store it in instruction register. For that, appropriate signals will be generated by control signal. Because of that, automatically the appropriate parts of your device, like example here, instruction register will be enabled, program count, so data will be, this memory location will be enabled, data will be transferred. It is unnecessary to understand all exact details, because you don't have idea how this control memory is created, right? At this moment, that's why let me postpone, but try to understand like a story. So what is going to happen is your memory will be taken like this, your instruction. Once instruction is taken, so then this load part will be studied by your control memory. Based on that, appropriate signals will be generated. Then automatically, a memory will be, that means this memory will be fetched, this memory, and that will be stored into register 1. All these things will happen while executing this instruction, right? Now you can see two phases. One is fetching the instruction, second one executing the instruction. So that two things will be done because of your control memory. Remember it, okay? There is just imagine like it's a circuit. Because of that circuit, automatically when that, so I can say like this. This is the circuit, control circuit. This is the input you are going to give. What is that? Instruction register. So based on the pattern of instruction register, what it contains instruction register? This instruction. So based on that, your control circuit will do the functionality. But why it will do, sir? Such a way we should design. We are going to design that in control circuit class, okay? At this moment, assume like this. So this part we are not discussing why it is doing. But what it is doing, I told you. What it will do always, first step it will do is, my dear processor, wake up. Go to program counter and fetch some instruction. It will fetch in the first phase. That is called fetching phase. Second phase. Then processor, please attach that to my circuit. Then that processor is going to attach. Of course, processor is also part of control circuit. So automatically we have to design such a way so that automatically this instruction register should be connected to this circuit. Then based on the input pattern, so we will be taking one decision. What is the decision? Addition or subtraction or multiplication or load or store. So if you can design this kind of circuit, that means then you are creating the processor itself, correct? So there are thousands of, these processor companies are, investing thousands of crores and in earning thousands of crores because of only this design, right? So that's why, do you think that it's very easy, like, today you attend the class and, tomorrow you start building the, processor? That is not possible. So your computer is very complex structure. We are understanding, details in a, lucid way. That means, so in a high level way. So some of the details we may miss because the original implementation may vary, right? But we are understanding the ideas. Example, I will ask you one question. So ask your brain what that, tomorrow what it is going to do. Okay. Otherwise, how your brain is going to work on some situation. Example, let's say you have, this is your brain. Tomorrow, suddenly, if someone asks you 1000 rupees, how your brain is going to work? It will say yes or no. Okay, something it will say. If I ask you, if someone asks 1000 rupees to you tomorrow, are you going to say yes or no? Who will decide it? Your brain. But how that brain is designed, that means, so can we know really it is going to say yes or no? It is a very complex structure, right? We don't know what is the behavior of brain. Similarly, this processor is also as complex as this brain, but we are going to construct it, right? At least, but because brain is complex than this one, so this design part we will be studying in control memory. I am not saying that we don't study, but at this moment we are just understanding addressing modes and machine instructions. So I would like to slowly give rough idea about, everything, so that you can understand the things clearly. But exact part, how to design a control circuit, that kind of stuff I will be teaching definitely in your control memory part. At this moment, our focus is mainly on how your program will be executed. Now by this time, now you will understand very clearly how your program is going to be executed. Very simple. In the early morning, so assembler first of all will load your program like this. Okay, that part we are not bothering. That means after that we will see what is going to happen. Now immediately, now we are seeing there is a program counter. With that program counter is filled with the starting address of your execution. Since you want to execute your program from here to here, that 100 will be loaded. Now automatically everything will be done. How, sir? First of all, always I told you, right, your control memory is designed such a way that what happens, it will do always two phases: fetch, execute. That's it. Fetch, execute. So in every cycle, so fetch and execute will be called. Like your control circuit says, my dear processor, fetch. Then automatically this instruction will be fetched into dash instruction register. Now you can easily understand the things, right? Load R1A. Now this load R1A will be given to whom? Control circuit. So it will understand that, it will decode it. This instruction load will be decoded and it will understand that, oh, I have to keep some data into register R1 and the data is given in the address of A. For that I have to go to A. Then immediately processor, go to A, I will take this address and go to this directly, this location which is 208, this is A. Then 5, fetch and give this to R1. This entire thing will be done because of the execution. Okay, so this such a way we have to design a circuit, that is control circuit, then only it will be possible. So but we know the output, what is going to happen. What is going to happen? Finally when this instruction is executed, R1 is going to get 5, remember it. Next, sir, now what is this program counter? 100. Again, if your control memory says, control circuit says, my dear processor, go and fetch the instruction again, then what will be fetched? 100. Then again same thing we will do infinitely, right? Do you think your machine is designed like that? No. Then what is going to happen? So in this execution process, we are going to fetch. You have seen two phases in the instruction execution. Fetch the instruction from the memory, execute, right? While executing, at some point of time, your circuit we have. So always the problem goes to here only. We have to design our control circuit such a way that what should happen? Your program should be incremented. You tell me, how much I have to add? 101 or 102. Sir, but I did not mention anywhere that program counter equal to program counter plus 4. How it will happen? This is not part of your program. It is part of control circuit. Okay, so that part we will be discussing later. But because of control circuit, automatically we say that that's why automatically. Nothing will be done automatically, but we say automatically it will become 104. Not because of your instructions, it's because of control circuit. Then now 104. Now immediately your processor will go to that circuit and says, yes, done sir. Then the control circuit says that, my dear processor, it's never ending process. Our circuit is designed such a way that I am designed such a way that I have only two things. I will ask you to fetch and execute, fetch and execute, fetch and execute. You blindly go to program counter, you will see one more instruction. Then, so that's why automatically, because of this circuit, this 104's data will be fetched, whatever it is. What is that again? Instruction. So, program counter again fetches another instruction, load R2 comma B. Now again processor will ask, circuit, what to do? Please give that to me as input. I will read it. Then the circuit will be decoding it. Then again it will understand that it is again a load instruction. Do whatever I tell you. So this control circuit is going to generate the signals so that appropriate registers will be enabled. Example, this memory location B will be enabled. Okay. So there will be a big circuit that, so there is one signal will go to this circuit, so this register, this data, let's say 7, that will be fetched, and already I told you. So if this instruction is executed, what are you going to get? 7. Okay. But technical details to happen that, what are the things we should do, we will see later. Okay. So finally, next, automatically in the execution phase of this instruction, 104 will become 108. That is automatic. It's not part of your instruction. Okay. Then again, this time processor will go to control circuit. Of course, control circuit and processor both are same. Just I'm using interchangeable. Just for good imagination, I'm dividing it into two parts. One is executor, one is servant, right? Now this servant will go to that circuit and will say, boss, what should I do? Go to program counter, fetch that instruction into instruction register. So again, another instruction will be fetched into, this instruction register, add R1, R1, R2, correct? Then again, so same question will be asked, my dear boss, what to do? Please give me that to me, then I will understand it. It is addition, I understood it is addition, and I understood addressing mode also. Then go to R1, R1, R2 and prepare R1 and R1 and R2 and add R1 and R2. For that, adder circuit will be enabled. So this control circuit will enable adder. My dear adder, please wake up. So one appropriate signal will be given to it. Then R1, R2 will be enabled, and that registers will be automatically converted to this adder. Such a way we should have circuitry. Okay. So then automatically the output will be connected to R1 so that R1 gets 12. Such a way we have to design our adder. Yes, we know already how adder can be designed, right? So we have designed adder, right? That adder definitely works and it gives output, and the cable we have to connect to the register so that the appropriate register gets the data. In that way, your instructions can be executed by your processor in a periodic way. Simple. Fetch, execute, fetch, execute, fetch, execute. Such a circuit it has. So all that fetch and execute phases are driven by, otherwise directed by a circuit called control circuit that we will be studying definitely in control memory. Very interesting thing that, right? Now we will be only understanding what is the model, how these instructions will be executed. Based on that, sometimes in the gate you can get the questions, correct? Now here our assumption is what? All the instructions are occupying only 4 bytes, okay? Because generally RISC instructions are specially designed like that, okay? They take equal size.